general and selective absorption. Then we'll be looking at absorption in different types of materials. And we'll be looking at something that is very interesting that we use a lot. We call it fluorescence. Then we'll be looking at some of the scattering effects. Then we will jump straight to diffraction, which is another interesting physical optics property. So that one we're looking at the principles. We're looking at something, and one instrument that we use we call the grating. We'll be looking at it. Then we're looking at how to derive using the single slit and other things. Then I think the last unit is about polarization, which we will end the class with, or this block with. So I'll still go through with the first unit, even if we've done it, because I'm sure by this time we've forgotten everything one way or the other. But it will kick in when I start. You'll remember some of the things that you've mentioned before. So we'll start with the unit 1, then we'll go to unit 2, then we'll follow that such. Then I'll share the slides if the class needs it. Then so that at least it will help us speed the class up a little. Any questions so far before I start with the slides? Okay, so I guess I'm good to start now.
So I
Yes,
want to find out the practical. So I don't know whether the practical you will teach you the same time on the online or will do it at the zero center, because some practical I try to do particular for.
Right. That's a nice question. I think we'll talk about this thing later. You are talking about physical optics practicals, right?
Yes, sir.
Perfect. We will talk about this thing later. We've been trying to push the agenda of the practicals, but we don't know how possible it is, because optics centers in Ghana is only UCC and Tech that has an optics center. So the things that you need for the practicals will be a little bit dicey. But let's see. I'll talk to my coordinator, Dr. Charles. Then we'll see how it will be done. Whether we'll do some pre-recorded videos to show the class, at least to see some of these things. The best is to maybe go to the optics lab and touch a prism, touch a grating, see how it works. Look at dispersion, look at fluorescence, polarization, look at it, so that at least touch a polarizer, know how it works. That will make the work interesting. But nevertheless, you'll find a way to go through. Is that okay? But those who at UCC, you can literally pass through. If you have a quiz, you can literally pass through my lab. I think those who are UCC, they've entered. I don't know if you've entered my office before. That is Laser and Fiber Optics Center. So it's an optics lab. So we literally can do everything pertaining to physical optics in there. Is that okay? So UCC people are safe, but the other centers, maybe unless we do a video and show the class. Is that okay? So like, can we go on? So we figure this thing out later. I'll talk to my coordinator. Okay. So let's look at the principle of waves. So I will start the slides like this when I'm about to teach waves. When we say wave, to either a literate or a layman, what actually pops into your mind first? Waves. Wave. What happened? What comes into your mind? Madam Priscilla, when you say wave, what comes into your mind? Madam Priscilla, are you online? Madam Patience, when you say waves, what comes into your mind? Am I online? Please, can you hear me?
Yes, sir. I can hear you.
Right. I'm online. Great. So, Madam Patience. Okay, Madam Priscilla is not responding. Madam Patience is not responding. Sir Bismarck also.
As I said,
Yes, sir. When we say wave, what comes into your mind? In all two perspectives, whether a layman perspective or whether a literate perspective, like what comes into your mind?
right. So please, I would say that waves a disturbance that travel through space or a medium.
Okay. Okay. Thank you. Sir David, when you say wave, what comes into mind? Sir David Edu. Okay. Say David Abrakwa Brown.
Sir, the disturbances that
Yes, sir.
travels
What
through
comes into mind?
the disturbances that travels through matter or space.
Okay. Okay. So that's a good submission from Sir Bismarck and David. Now, I'll talk about this one later. But yes, Sir Lucky.
Yeah,
Yeah,
like
Sir
this,
Lucky.
a disturbance that travel through space. Yes, sir. You see, it's a disturbance
Yeah,
that
I'm
travel
listening.
through space or matter, and that allow that travel. It travel through matter. Disturbance that travel, which allow energy to be conveyed from one point to the other, but it does not move by
Okay.
itself.
Okay.
It
So that's it.
convey energy from one point to the other.
It doesn't move by itself. Okay. Okay. Perfect. So this is very interesting. To when I'm to explain wave to a layman, I can give a very simple illustration. Like when you see you have water in a barrel or in a pan, in a big pan, of course, and you see how stable the water is. You know, the water has settled to the point that it's just thinking about itself until maybe you use your hand to touch the middle. And right after touching, you see it creates some ripples from your starting from your hand. Then it starts moving to the end of the barrel, you see, like the picture that I've shown here. Or let's say you have a pond that has a very surface that is settled. We are not talking about a surface like a sea, the ocean waves. Let's forget about that for now. We are talking about the normal pond that has a face settled. Then I touch the surface. When I touch the surface, one or two things comes into mind. Am I actually moving the water? What am I transferring from my hands that I've used to touch the surface at the center, and what is actually moving towards the tip of the barrel? Is that okay? So that is actually wave in simple terms. Is that okay? So we've caused a disturbance. One, two. What after causing the disturbance? What are we transferring? Is that okay? And the disturbance is caused in a medium. Here, the medium is the water. It's a liquid. Is that okay? And what are we transferring? Is that okay? So that is the whole perspective about waves. Very interesting. Because of waves, we can literally do everything in this world. Is that okay? We cause a disturbance for something to happen. Now, when we see something like this, you know, after touching the surface, like a typical pond that I've used as an example, or you see a settled pond and you throw a stone at the center, then you see that ripple that start from there and comes to the shore. And there are some things that happen there. The ripple that we are talking about is that round thing that is starting from your finger or the stone that you've hit with coming to the shore. That is what we are calling the ripple. We can bring some characteristics of this ripple. So we can call the ripple, we can call the highest part as the crest, and we can call the lower part as the trough. In fact, we can derive a lot of properties from it. But now let's keep something like a crest and a trough in mind. I'll actually visit this thing again. Now, when we are talking about these applications, they are enormous, particularly faculty has messaged me. Class, excuse me. Sakode, you just messaged me, but for some reasons I can't read the message. I don't know. It's not showing on my at my end here again.
So he was asking if the class is being recorded, but it is being
What
recorded.
is Sakode saying?
He was asking if the
Yeah,
class
it's
is being
being
recorded.
yeah, they are recording it. Okay. Excuse me. Thank you. So now, when we are talking about the application, they are enormous, like a lot of them. Is that okay? Now, depending on where this disturbance is caused in, we can give a terminology for that kind of a wave. Is that okay? So we have a disturbance that is caused in water. We have a disturbance that is caused in in a solid, like the earth. So we hear something like earthquake has happened. It's a disturbance in a medium. Is that okay? We hear that no, you are beside me. I talk. You can hear. Is that okay? It is a disturbance that my voice, or after talking, it has caused the gas around it to transfer some form of energy. Is that okay? To your ear. So they are all forms of disturbances. Now, you can actually go to the hospital, then they have something they call the transducer when they are using ultrasonic waves. Say a lady is pregnant, or they have to diagnose, even a guy, they have to diagnose your level of kidney issue. You go lie down, they put some gel on your tummy, then they press the transducer in your tummy, then this transducer sends some form of a wave to your body, then the back signals is being recorded, then we see what is going on. In fact, right now, if even after some short weeks of pregnancy, you can even determine the sex of the child. And this is all because of waves, And there are a lot of applications of them that we can't even think about. Now, the motion that we are talking about, when we talk about wave motion, we are talking about the deviation from equilibrium. Is that okay? So when it is at rest, when we moved it, whether we moved it up or down, we moved it left or right, we've still deviated its equilibrium state. Is that okay? And that is what wave is talking about. So let's just keep that one in mind. Is that okay? Anytime we causes a disturbance. So anytime you talk about wave, the first thing that comes into mind is the disturbance that we've caused a state that is in an equilibrium. Is that okay? Or at rest. That is what we call as a wave. The other things adds up. The other thing that adds up is it the energy we are moving, or we are moving the matter, and other parameters. Is that okay? But the first thing that has to come in mind is the state of equilibrium that we have disturbed. Is that okay? So that disturbing of the state of equilibrium is what we are calling as wave. So let's keep that one in mind. Very, very important. Now, I mentioned some characteristics of waves. The first thing is that we can talk about is the medium. You can talk about the energy transfer. We can talk about the particle movement. We can talk about the periodicity of it. Is that okay? If we have these characteristics, we can also define the wave. Is that okay? So after causing the disturbance, where are we causing the disturbance at? It needs a medium before we can cause a disturbance. Is that okay? And when you're talking about a medium, you're talking about a solid, a liquid, a gas. And even with a medium, it can also work in a vacuum. Is that okay? So it is very important. So where is the wave happening? Is the wave happening in a solid material like the earth, or is it happening in a liquid material like a water? Is it happening in a gas like the cars we have around us, or is it even happening in a vacuum? Is that okay? Now, after we've caused a disturbance, this medium is transferring something, and the transfer is what? Is the energy. Is that okay? So we have to also keep that one in mind. So we are moving one energy from one point to the what? To the another point. And I think that is what Selaki was saying. Is that okay? So anytime there's a disturbance, anytime there's even earthquake, there's a form of energy that is being transferred from one end to the what? To the another one. Is that okay? And interestingly, one thing that we have to keep in mind is there's no net particle movement. So in as much as there's a transfer of energy, it's not like you sending a child, could you go and buy me a granite from this shop? You know, if Kojo is a particle, one way or the other, you are sending the particle to go get energy for you or to send an energy for you. But wave doesn't behave that way. Itself doesn't move, but it will move an energy for you. Is that okay? So it's typically like we have a lot of them. You can imagine a lot of Kojo in line to the shop. Like we have Kojo prototype, like 100 of Kojo, and they form a line to where the shop is. So if you tell Kojo, Kojo, go and buy me, let's say, a granite, what Kojo has to do is to pass what you've sent him to buy to another prototype of Kojo. Then he will send to another prototype of Kojo. He will send another till they get to the shop, get what they want, and also forward it to you. I don't know if the scenario I'm creating you're understanding. So you can imagine we have one Kojo here. And we have another Kojo standing here. And we have another Kojo standing here. So they are all following up, a lot of Kojos following up. So we get to the shop that we want to buy something. So another Kojo is standing here. Is that okay? So all this space is filled with Kojo. Then this is your shop, your house. And you want to send Kojo to go get you something. The traditional way or the normal way of life living, we know Kojo have to walk, go and buy the thing and come back. But waves doesn't behave that way. What wave will do it? Because the wave itself, it don't have to move. Is that okay? So there's no particle net movement. So what Kojo will do is, after sending Kojo go and buy me granite. Kojo will send the next Kojo, go and buy as granite. Next Kojo, go and buy granite. So we get to the last Kojo, he buys a granite, then he also sends it back like this. Is that okay? So it gets back to home. So you see, in as much as there's a movement, the movement is telling the other particle to get what we want. But the particle itself doesn't move with the energy and send and go and get the energy for you or send the energy for you. Am I making a little sense with the scenario? Okay, perfect. Is that okay? So the particle itself doesn't transfer the energy. The particle movement is not related to moving an energy. Is that okay? So what is we are talking about is there's no network particle movement situation in this kind of a wave. Is that okay? And another thing is there should be a level of periodicity. So you saw how the ripple were behaving. When a stone was dropped on a pond, the ripple was behaving like this. Is that okay? It is something like this. We call it's a repetitive pattern. Is that okay? So you see the same level of pattern that is happening. So you see when Kojo was going to get the granite, when he sent the other Kojo, the way and the gesture that he used to send another Kojo is the same one they are all using. So maybe he will move his right hand, buy us something. Another one will do the same thing, buy us something, buy us something with his right hand. Is that okay? So there's a level of repetitive pattern that is actually going on. Is that okay? And that is what we are talking about it when it comes to wave. So ideally, when we define wave, all these things should come into the definition. Ideally, is that okay? Now is it final year? So our definition of wave is supposed to change a little, and with our understanding should change a little. Is that okay? We are not going to define it as we define it way before doing general physics and doing introductory atomic heat and optics. I'm expecting us to elaborate on wave definition with all these characteristics from waves. Do we understand?
Yes, sir.
But let's make sure that when we are defining, don't bring Kojo situation. Just use physical good terms. Is that okay? I beg. A Kojo situation is for your understanding. Okay, now let's look at something here. Very, very important. Now, we can also categorize some properties that we will get from waves. And I told you that there's a level of repetitive patterns that is going on, the periodicity of it. So it generates some properties. And one particular property is a wavelength. One particular property frequency. One particular property is the amplitude. One particular property is a speed. We will go through all these very soon. Like very, very soon. But I'll break now, then I'll come back. Now under waves, have common types. In fact, the type or category of waves depend on how you are defining it. Is that okay? If you're defining it based on medium, we have two, that is the mechanical and the electromagnetic. The level of propagation, then we are going to define it transverse or longitudinal. Is that okay? So we have longitudinal waves and transverse waves. If you are interested in the medium, we will have something we call the mechanical waves and the electromagnetic wave. And I'm sure this thing we all know already, but we are just adding it up again. Now we will look at the transverse and the longitudinal. But for the medium, when you are talking about particularly mechanical waves, we are interested in the matter of propagation. Let me say it that way. Is that okay? The solid, like liquid, and the gases. In fact, mechanical waves need a matter before it can travel through. Is that okay? If you give it solid, perfect, it travels through. If you give it liquid, perfect, it travels through. If you give it gas, perfect, it travels through. Is that okay? Whatever being the case, it needs a medium. You understand? Whatever being the case, it's like a child. Whatever being the case, it needs a parent. Before it can function. It needs a teacher before it can grow to become learn a profession. It needs a guardian. So whatever being the case, unlike the electromagnetic waves, it is good without a medium. Is that okay? Even if there's a medium, it can still propagate through, but it is still good without a medium. It doesn't need any medium at all. Is that okay? So, and a typical one is light. A typical one is the radio waves, microwaves, X-rays, and the gamma rays. Is that okay? It is fine without a medium. It can easily propagate. And if you remember, I even made a demonstration where when the Earth is here, we are on Earth here, and the sun is here. Sorry about my drawing because the sun's supposed to be super bigger than the Earth. Now, we have the sun here, we have the Earth here. On Earth, we have a lot of gases surrounding us. Is that okay? Different layer of the atmosphere comes. And right after some layers, the next thing that we have above is something like no gas area. Is that okay? So let's say all the atmosphere's issue ends around this level of the atmosphere. Is that okay? The next one that we have here is no gas is there at all. Now, the interesting thing is, if no gas is here, no gas around this end, the question is, why do we get the sun reaching the earth? Can someone help me with this? Why do we get the light reaching the earth if there is no gas at all? Let me say, no medium at all. But the sun is reaching the earth. Why? This is a question for the class.
So,
It means it's traveling through empty
Yes,
space, or it can travel through the empty space.
because perfect. It means the wave is traveling through what? A vacuum or the empty space. Is that okay? And a typical one is it means that particular wave traveling through the empty space or the vacuum is the electromagnetic wave. Is that okay? It doesn't need a medium. Gas or no gas, it will still travel. Is that okay? And in fact, even the sun that we see there, as it is burning, I said the last time that it makes some noise. It's like you burning something in the house. You see that the sound that it makes. The sun too is making that same sound. But interestingly, that sound doesn't reach the earth. And why is it like that? Question for the class.
So
I can't hear the sound.
I think sound needs a medium for a material medium for its propagation. So since there's a vacuum, the sound cannot travel and reach the earth.
Perfect. Is okay. So the sound waves that we have here is a mechanical waves, and it needs a medium to travel through, a medium like gas. Is okay. But outer space, there is no gas here. So automatically the sound blocks us. Is okay. So there's no sound coming to us at all. But at the end of the day, the light will reach us. Is that okay? So when researchers go outer space, they don't communicate. Let's say when they are on moon, they don't communicate by saying, "Hey, what is going on? Do we have to go for lunch?" They will not hear each other. They have to communicate through radio waves. Like they have like talking on phone. Let me say it that way. Exactly. So they are all in their small chambers that they can talk on phone. So they need a different form of communication level. Because when you see your partner and you talk through the gas for your partner to, the partner will not hear. The partner will just see your lips moving up and down, but the person will not hear anything. Is okay. So this is very interesting. Now let's talk about the propagation level. I told you how Kojo, we were sending Kojo to buy us a granite, and we have a lot of Kojo in line. So when we say Kojo buy us a granite, the first Kojo sends the second Kojo, the second Kojo sends it. So they are not moving, but they are just sending each other. Now, let's say the money we've given to them is the energy they are moving. Okay. In fact, Kojo has to make some level of movement before that energy can be transferred to the last end. Is that okay? It is very important. Now, that repetitive manner is what we are coming to talk about here. Is it that they are moving their hands parallel to the energy movement, or they are moving their hands perpendicular to the money movement or the energy movement? Is that okay? And that is the propagation we are talking about. If their movement, Kojo's movement, is parallel to the money, let's say where the money is going, that is where their hands moves before the energy can be transferred. We have a name for it. But if their movement it is perpendicular to how the money was moving, we have another name for it. Is that okay? And that is what we are calling a longitudinal waves or a transverse wave. So a typical example of a longitudinal wave, like this thing that we have, is the movement of particle is what parallel to the what the motion of the what of the energy. So if I move my hands, next could you buy me something? 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 It is parallel to the money movement. Is that okay? In a situation like this, I am calling it what a longitudinal wave. But let's look at something. Supposing if Kojo has to send the next person, and this time around, anytime they are sending, they jump up and down. It means their movement is going to be perpendicular to the money movement. So you see, the money is straight. Let me show you what I drew earlier. The money is moving straight like this to the last Kojo. Is that okay? If they move their hands to pass the money, it means that they are moving parallel to where the money is. Let's imagine the money as our energy. Is that okay? And when something like this, wave. But in a situation where before first Kojo sends the second call, he has to jump up and down. In a situation like this, you see, perpendicular to the money. And in a situation like this, where we are calling it what? A transverse wave. So the movement of the particle are what? Right angle or perpendicular to the what? The motion of the what? Of the energy. So if Kojo is sending the next Kojo, he will jump down, buy something, up and down, buy something, up and down, buy something, up and down, buy something. A typical example is the transverse wave. And now we mostly use, and you are understanding at the other end. You know, when you move up and down at the other side of it, you're actually moving perpendicular, let's say up and down. The propagation of the wave is going to be on where the road is going to. In a situation like this, we have it the perpendicular to the what? The motion of the wave. And of course, if the motion is this end, it means the energy is in this way. So it means the particle is moving to the what? To the wave. And it's that we're calling it what? A transverse wave. Are we getting it a little? Perfect. Now, the application, they're enormous. Is that okay? We have a transverse wave, we have a longitudinal waves, and a typical example is the sound. We have the typical example is our, our light. Is that okay? Now, there's a lot of applications. A lot of applications that everything now is wave. Like anything that you can think about. There's a level of application of wave in there. Is that okay? Anything you can think about. To your room that you are listening to me now. So I don't know where you enter, anywhere that you can think about, that you go, to the hospital, to workplace, teaching area, anywhere, to your school. My network. Yeah, hello class.
Hello, sir.
Hello.
Hello, sir.
My network is messing up, but can you see my screen?
It's misbehaving.
Yeah,
See,
just that it's not clear.
it's not clear. Yeah.
Okay.
It's Blair.
Hello, class. Is it better now?
Yeah, it's okay, sir.
Yes, please.
Okay, perfect. I didn't go to the office this morning. I'm in the house, so sorry about that. Talking about the application of waves, they are enormous. You know, it is very interesting that I don't have to open a bag that a traveler is using, but it, I can let you pass through a system, and then I will know what is actually in the bag. Very very phenomenal, you know, and it's very interesting too. Now someone gets an accident, then the person can literally just enter hospital. You lie down or sit down, then there's a machine that gets close to you, and we can know internally what is actually going on in your body. Like, so interesting. Is okay. And these are all the application of waves. As of now, we can 100% predict the sex of a child within a week. You know, very very interesting. And these are some of the things that the world is growing up to. And I'm sure there's a lot of discovery that waves is going to bring. You know, the last time, I think I was telling, when I was teaching introductory heat and optics, I think I mentioned this. After COVID also showed us a level of intelligence. After COVID, we started using something like the infrared thermometer. Is okay. And these are a typical example of wave application because our body emits some form of radiation. And what the infrared thermometer is doing is to pick that radiation and convert it to heat for us. Is that okay? Because first, the thermometer that we used to use, they have to place it in your armpit, then you close your arms, you press it against it a little, then a beep comes within some seconds. It means your temperature has been read now. I stand to be corrected. That was what we were using before, right? Oh,
Yes.
perfect.
Yes, please.
Then now, right after COVID came, we don't have to get contact with instruments. So now the infrared thermometer came. It means scientists think to that extent. Now say, oh, our body is emitting radiations. Why don't we get something, a detector to just pick the radiation? Because you will know this formula later. I'll show you. We call it the relay displacement formula. Then there's a formula that relates the wavelength, that is the radiation, and temperature. So if I have a kind of thermometer like that, and let's say an ion is burning, it can pick the radiation as in the color and convert it to temperature for me to know the exact temperature of the ion without necessarily bringing a typical thermometer to measure the temperature of it. Is that okay? Just a matter of radiation and color. Is that okay? It picks it, converts it to temperature. Right. So it is very interesting what wave has brought us to, you know. Now, military people, they don't need to necessarily go to war daytime. At night, they are very fine. There's their infrared cameras that they are looking through, and they can snipe anyone down. And when you are at the comfort of your sofa, you can press something for the signal on the television to change. You don't want to watch UTV again. You want to watch Adum TV. You press, then it change. And these are all radiations, just a small signal that the remote is sending to your television. Is that okay? And that is all. You are good to go. Now, even Apostle Kojo, Sopho Kantanka also brought something where you just have to clap, then the television goes off. They are all part of these waves. You know, you have to shout and something moves, because at the end of the day, we are causing a disturbance. So if you're able to read the normal partition of the disturbance and any different changes that has happened, and you place a detector in there, it is good to pick it in for you to get what you want to do. Is that okay? So these are all some of the applications. And in the field of research, that is what my lab is doing. So when you look at even my research, you look at, I'm sure you've met Dr. Peter, you've met Dr. Charles. We are all into field of researches like this, using this typical application of these waves. So when I am teaching, maybe in the next 2 weeks or something, I'll show you or talk about something we call the spectroscopy. That is what we deal with. It's just a normal light matter interaction. Then we pick these signals. Is that okay? Very, very interesting. So waves has numerous applications. Is that okay? Now, if we don't have wave, I'm not sure we can survive because I don't know how you communicate and other things. So it is very, very interesting. Now, let's jump straight to simple harmonic motion. Now, we've been talking about how periodicity the wave can be. Is that okay? A typical characteristics of a wave. Now, talking about a simple harmonic motion, we can also relate that one to in that perspective. But there's a little changes here. The periodicity motion still is in place with a simple harmonic motion. And of course, there should be a particular central position. Is that okay? Where we are sliding from one end to the other end. So I am sure we are all familiar with the 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 simple pendulum experiment, where we place a thread and a ball at the tip. Then we give a little length. Is that okay? Then we move the ball at a very small angle, like very, very small angle. We are talking about, let's say, 5 degrees. Then we leave it. Before moving the ball, that center that it was, that is what we are calling our central position, right? Then after moving the ball, you see it moves from one end and swings to the another end and swings to the another end. And so you don't touch it again, in fact. You see, there's a periodicity level that is going on there, like periodic motion moves up and down, up and down, up and down, up and down. It doesn't need your strength again. Is that okay? A typical level of what? Simple harmonic motion. So when you look at the definition that I've placed here, it is a periodic motion, one, through a central position, two, so that the maximum displacement at one end equals the maximum displacement at the other end. Is that okay? So it goes left, that is the maximum displacement. That displacement that we had initially, when it goes to the other end, we should expect the same displacement there. In fact, we can relate how the periodicity of a simple harmonic motion to our normal wave, because it's also a form of a wave happening. And that is what we have here. You see, just in case we are not moving at a small angle and we want to consider a full cycle movement, we can relate a full cycle movement to a full wave like this. Is that okay? Where we started here to where we ended here. And we know that anytime we complete an end like this, we have completed a half cycle. Anytime we completed another end like this, we've completed another half cycle. Is that okay? So this is a full cycle, in fact. Now, we can also relate this one way or the other when talking about moving. You see Hooke's law, when we have a particular force that we have to move a displacement. Is that okay? There's one Hooke's law formula. You see, Hooke's law relates particularly the force and the displacement. But there's also one experiment where we load some let's say weight on some spring, helical spring experiment. I don't know if you did something like that. Then we move it downwards and we get a vertical oscillation instead of the normal horizontal oscillation from a simple pendulum. Is that okay? We can also relate it in this perspective too. But this time around, our displacement is not going left and right. Our displacement is moving up and down. Is that okay? Very, very important one. We can actually deduce a formula. I want to just move to the formula. Hold on. Very good. We can actually deduce a formula from this, where we can relate the amplitude, we can relate the displacement, and we can relate the time, and we can also relate the phase difference. Is that okay? We'll go through all of them. Now, if we are relating the displacement, we can of course consider the fact that we have a wave number, and we can consider the fact that we have something like the angular frequency. Is that okay? So it all relates to it. So the displacement relates with the wave number, and the angular frequency relates with the time. And we have our phase difference. Is that okay? And A here is our amplitude. Is that okay? We are talking about the maximum displacement that we've gotten at one side. Now, let me go back a little. Now, let's look at the properties that we've derived from the simple harmonic motion. Now, we have our crest and trough. Is that okay? So this particular end is the crest. The maximum point at the top here is the crest. The maximum point at the down here, it is the trough. Is that okay? Now, if we want to measure the time that we've used from one maximum end and another minimum end, we can relate it with something we call period. Is that okay? So we want to know, okay, within a particular time, how many cycles have we completed? Is that okay? We can relate it with period. So period, when you look at the definition that I've written here, it is the what? The time for one complete what? Oscillation. So after going run like this, how many seconds did you use? That is what we are interested in. Now, period and frequency is very, very related. Like very, very related. And when you're talking about frequency is looking at the number of oscillations this time around you've covered within a particular time. You see, period was looking at the time you've covered, but frequency is talking about the number of oscillations. So within a seconds of K, how many oscillations have you covered? And that is what I'm going to define as what? As my frequency. And of course, the unit is hertz. So before this one, we were doing electronics. And I think you did the theory part, but the practical part, I was showing how, with my UCC centers particularly, I was showing how even wave, when you're talking about when you're talking about the energy that we get from ECG, it is also related in terms of frequency because it is voltage with respect to time that is coming to us. Is that okay? So the energy is coming as a sinusoidal form, that is coming to us. So even at that end too, frequency is much related. And that's just by the way. So now we can also relate something we call the wavelength, where wavelength particularly talks about the distances between two adjacent, let's say crest or trough. Or maybe you can just define it, the distances that we've completed for a cycle. Exactly. Because this is a crest. But let me use a different waveform. So if we have something like this, and this is my wave, we are talking about a crest here and a crest here. Is that okay? So that distance from here to here, that is what we are calling a wavelength. Is that okay? Or let's say a trough to a trough. That is what we are calling a wavelength. But let me ask the class a question. If I start my wave motion from here, is that okay? I am drawing beneath, so let's look there from here. Then I come and end up here. So let me write this place as 1, and I come and end up here as 2. How many cycles have I completed so far?
Half cycle.
Very good, half cycle. Do we all agree to that?
Yes, sir.
Perfect. So that is a half cycle. Even when you look at the distance that I've placed up there, you see when the ball was going, it starts from here. It goes to complete here. That is where the half cycle has completed. If it goes round, it means it have completed half and another half again, making it a full cycle. That is 2 pi or 360 degrees. Or if you are doing it in radian, 2 pi radian, right? Now, if I start from 1, goes to 2, then come and end up here as 3. How many cycles have I completed?
A full cycle.
I've completed full cycle, thank you. So I start from here, goes, I end up here. This is half. I complete another half here. It means I've taken what? Full cycle. But let's hold on. Let me ask another one. If I start from 1 and I come and end up at 4 here, the top here, how many cycles have I completed?
A quarter.
A quarter cycle.
Yes.
So from here to the top here is a quarter cycle.
Quarter.
But what if I start from 4, then I come and end up at 5? So the top here. So the crest at the top here and another crest at the top here. How many cycles?
1.
Very good. Look at the full cycle or 1. Is that okay? So it means I have a quarter here, I have a half here, then I have another quarter here. Is okay. So the quarter adds up to the initial quarter, getting a half, then another half here. Then I get a full cycle. So wavelength is talking about the distances that we have complete for a particular full cycle. Is that okay? So whether you are defining it as a crest or as a trough, or you will define it as starting from 1 and ending at 3, they are all wavelength. Is that okay? So we want to know the length that we've completed for a full cycle or only one cycle. Is that okay? So starting from 1 to 3, I've completed one cycle. Starting from 4 to 5, I've completed one cycle. Now, we can actually relate wavelength, we can relate the period, and even come and relate the velocity of it. Sorry about the spelling here. Wavelength, V is here. So if I want to relate velocity, wavelength, and period, the formula is quite straightforward. It's velocity equals wavelength divided by period. And you know period is related as frequency in the inverse manner. So if you want to ignore a period, we can just come and multiply the wavelength by frequency. And that is what we have here. It's okay. This formula is very, very important. So I beg, let's keep it in mind. And most of the times you see it as wavelength relating velocity relating wavelength and frequency. Is that okay? They mostly don't relate the period. It's most of the times the velocity, wavelength, and frequency. Should we go on? Perfect. Now let's look at something here. We can also observe sinusoidal as this. In fact, when we have let me show you something. This thing is not opening. I wanted to open something to show you, but let me just try and explain. So if we have X, and I think the last time my group came here, I was telling them that if you have X and you have some values of X, say 1, 2, going up to, let's say, 20. So 1, 2, 3, up to 20. Then we have Y. But Y relates to an equation like C sine X. So anytime we want to look for a corresponding value for X value as 1, what you have to do is come and put the value 1 in replace with where the X is, so that we get the value for Y. Is that okay? So at the end of the day, if we are mapping, we will get a value for 1 correspondent, 2 correspondent, 3 correspondent, up to the 20th correspondent using this equation. Is that okay? So just come and put 1 in here, 2 in here, 3 in here, 4 in here, then get values for Y. Now, when we are done, then we want to plot the two of them. We should get a sinusoidal waveform. Very important. The behavior of this sinusoidal waveform with respect to how a wave behaves That is why we always relate sinusoidal and what? And waves. So wave behaves like this already. And if we are looking at mathematics level of trig, all the signs that behave like a wave is a sine wave. Is that okay? So anytime you hear about sinusoidal, mathematically it's an expression that can be used and have a typical waveform as we have for the wave. Is that okay? So we have it as a sinusoidal waveform. And I have even stated it here because the curve is the same as that of the function of sine plotted against what? Against t. Is that okay? But here I'm using x and y. So this you can actually try it up. You get a lot of values for x. Then you use an expression of sine x. Is that okay? To derive another set of values for say y. Then you plot the two of them. I'm having this programming software. I wanted to use it so that we get a very nice pictorial of it. But maybe I'll do that this time that we meet, then I'll show you so that I don't waste time. So this is very important. Now, even if we have uh, our body is standing at one end and we are holding a rope like the one I showed you earlier, then we move it up and down, we still going to get this form of a sinusoidal wave. Is that okay? Now, I've shown you this equation before, and this equation can be derived in other forms because this wave number has its own formula, and the angular frequency that we have here too has its own formula. And the wave number here, the formula is 2 pi on lambda. 2 pi on lambda. And the lambda here is wavelength. Is that okay? And that angular frequency is related to period. So we write 2 pi on t. On t. So in a typical waveform like this, we are interested in the displacement and we're interested in the time and we're interested in how the wave behaves relative with the other one. That is where phase difference comes in. This one comes in. Is that okay? And when we are related it with distance, I told you wavelength is talking about the distance that we've completed within a particular cycle. So you see the distance x is relating to what? The wavelength, that is the lambda. When we are talking about this, we are interested in the time that is going on. So the distance of the wave, the time that it has used to complete that particular wave, the period comes in. Is that okay? So we have 2 pi divided by what? By period. Right? So if we ignore the wave number here and we ignore the angular frequency here, then we substitute their formulas in there, we should be getting something like this. Is that okay? Can we try it? Then you confirm if we are getting this for me. Maybe a minute or two. So substitute this one in here and substitute this one in here and show me what you are going to get next. Hello class, are we online?
Yes, sir.
Okay, so please let's try it up right now. Substitute this formula in here and substitute this formula in here. I beg, are we done? Oh, we are still on it.
Yes, sir.
Okay. Madam Patience, are you trying? Says
I had, I had a third equation rather, the third one.
Okay, perfect. Madam Patience.
Sir, I'm still on it.
Okay, so we are trying to confirm if you get exactly what we have here. So we are substituting the wave number and the angular frequency in the equation to see what we will get.
So I had the third equation, not the second equation.
Okay. I'm waiting for Madam Patience to finish, then we'll continue.
Hello, sir.
Yes, Sir Philip.
So when they get a third equation, then you substitute the value of the period. That T equal to lambda over V. You get the second equation.
Oh, okay. Yes, that's true. So when we get the third equation, this third equation, they will come and substitute this in here. We make
Yes, sir.
T the subject. We make T the subject, the period the subject, and come and substitute. Then we get the second equation. And that's very true. Please let's all try this thing up. I beg. Just try the equation, do the substitution, and follow up what we are doing. Just confirm if it is the equation that we're supposed to get. Is that okay? So after getting the third one, try and substitute the period. Make T here the subject. Then after making it the subject, you just substitute it inside here and see if you get a second equation. Please, any update? Madam Patience.
Sir,
Yes, please, any update?
sir, I got the third equation, but
Do the
I'm trying
second
to
one.
replace it with the this one to get the second one. So
Okay.
it seems
But apart from,
so should I
okay,
multiply? I will multiply the T on the other side, then I'll cancel it to get the second one. Or
so
yeah.
you will make T the subject here
Yeah.
so that you get lambda on V. And here,
Mm,
this particular V that you see here, it is frequency. It's not
yeah.
velocity. So let's just keep it in mind. Is that okay? Then,
Mm,
oh, sorry, it is velocity rather. It is
velocity.
sorry.
Mm,
It's velocity rather, yeah, not frequency. Sometimes we make it frequency, but this is velocity. Sorry. So we have it lambda on velocity V. Is that okay?
mm,
Then we come and just substitute this whole thing at where the T is. So we ignore the T and just put it. But you see, there's a lambda here, there will be a lambda here.
a lambda there.
So very good. So it will bring a lambda out one way or the other somewhere. So try it up in this. Perfect. Is that okay? That's how we managed to get a lambda at the denominator here.
Mm.
Okay.
Apart from Sir Philip, are we all done, or we are also doing it still?
So I've gotten it.
Perfect. Sir Schizo. Sir Mohammed. Hello, Sir Mohammed. Okay. Sir David. Kindly update me. Are you done?
Hello, sir.
Yeah, are you done?
Yes, please.
Okay, so we are confirming all the equations. Is that okay?
Okay.
So now let's look at something. We can also find the derivative of the wave equation to get a velocity. You know, this times you find derivative, we get velocity. When you find the derivative of velocity, what do we get? Question to the class.
Acceleration.
Acceleration, perfect. Is that okay? So when you find the derivative of the first one that was related to displacement, we are getting velocity. So when you do that, this is what we are going to get. And the first term that we were having before, that was the displacement is going to go out. Is that okay? So it will be left with only the angular frequency multiplied by the time, which of course we know angular frequency is related to 2 pi over the period. So you can just substitute it here. This is just by the way to show us that we can relate velocity with respect to what time. First, it was just the displacement here with respect to what time. Now let's look at one important thing that we call the phase difference. Phase difference will not end up only in today's class. We may see it one way or the other in another section called interference. So let's keep it in mind. Now, when we are talking about phase, we are just describing how the wave is moving. Is that okay? At which point particularly is the wave is, so if we have our cycle behaving something like this, the waveform, and we are talking about phase, we want to know which point particularly is the wave is on this particular cycle. That is what wave is talking about. So now phase difference comes in when we have two different waves traveling. Is that okay? So we want to know whether they are in phase or they are out of phase. Are they at the same point or they are not on the same point? Is that okay? And we want to know how they deviate from each other. And that is where phase difference comes in. So anytime you hear about phase difference, we are literally interested in two different forms of a wave. Is that okay? Only one we can determine phase difference. We have to get two. That is why this equation, we have two wave equations. So for wave one and for wave two, we can look for the phase differences between the two waves. Is that okay? So if I am interested in finding the phase difference between the two waves, I need the phase constant of this wave, and I need the phase constant of this wave. And if I find the differences, of course, I can find the phase differences. Is that okay? And as I explained earlier, we have our displacement here as y, and we have our amplitude here as a, and we have this place as our time. Is that okay? It means as the wave is traveling on the horizontal path, it is very, very dependent on time. Is that okay? Very, very dependent. Now, the whole situation is with the phase difference. We want to look at whether the two waves are started at the same time, or when they started, one went ahead than the other one. Like, let's say one started within some microseconds or milliseconds or picoseconds, another one started again. Is that okay? So it's like we running on a field, like a typical standard football pitch. Then you see the track, they have a particular, because how the track has been designed, the outer lane has more distance to be covered than the inner lane, So anytime they are running, those who are the outer lane, I'm talking about the athletes, those who run around the pitch, and let's say they are doing a 400 meters, the outer lane is supposed to, the one taking the outer lane has to take a long distance. Because of that, when they are about to start, the person on the outer lane has to move forward a little, about, let's say, 10 meters before the one in the inner lane follows, before they start the race. Is that okay? Ideally, you can imagine it as this, where we have one phase that is starting before the other one. Is that okay? Because of that, they will not be in phase. Is that okay? So when they start, it means we can look for the phase differences between the first one and the second one. Now, there's a formula for this, which I'll show you later, which relates the period and other things. I'll show you later, and the time. But let's look at something that we are saying is in phase. When it's in phase, this is how the two waves behave. So this is my y, and this is my amplitude, a. You see, when they're in phase, they are literally overlapping each other. Is that okay? They started the same.
Hello, sir.
Yes, and Madam
Hello,
Ernestina.
sir.
Yes, madam.
Hello.
Yeah, hello, madam. Can you hear
Sir,
me?
please, I can't see your screen. I don't know if it is from my end. I don't know.
Oh, sorry. Is it the same for everyone?
No, I can see.
Mm.
Okay, I can
So,
see it
Madam
now.
Ernestina, you can see it now. Perfect. I'm sure it was your network. Okay. So now, if they are in phase, the two waves started at the same time. Is that okay? So they are actually overlapping. They have the same properties. Is that okay? When you look at the equation, the x and the y, everything is the same. The time, everything is the same. And even the phase too, it is the same. So you see, we have a wave of A, and we have a wave of B. But you see, wave of A and B are in the same phase. Because of that, they are overlapping on each other. When I say that they're overlapping, like back, so exactly. Is okay. And here you cannot even see the B, because the B is black. Is okay. So the B is black there, and the A is lying on top of it. Is that okay? So a situation like this, we call it that they are in phase, the two waves. Can I get a thumbs up if you understand? Perfect. Now, yes, Sir Samuel.
Say, please, oh, what would be the condition? What would be the
Mm.
exact condition when these two waves are in the phase?
Oh, okay. That's a nice question. So you see, the wave equation determines how the wave is behaving. Is that okay? So if I know the amplitude, I know how the height of the crest or the trough has reached. If I know now the k, we know the k is related with respect to 2 pi over lambda. And now we know lambda relates to the distance that a cycle has behaved. So it means if I know a value for k here, I can know how the distance is going to be for a cycle, like whether it's going to be a long cycle or a short cycle. Is that okay? Whether it's going to be as small as this or as big as this. And if I know the time too and the values of the time, I can also know how to how the wave is going to be drawn. So literally, this equation values can tell us how the wave is supposed to be. Is that okay? But now we are relating one wave to another wave. And now when we are relating, that is where the phase constant comes in. So the condition is very dependent on one, the parameters that we have here for a typical standard waves, and two, the wave numbers value for the A and the wave value for the B. Is that okay? If the phase constant is 2 here and it's another 2 here, voila, we will say they are in phase. Is that okay? So it's just dependent on the value that we have for with A and with B. And we are saying that anytime they are in phase, it means they have the same phase constant value. Is that okay? So where they will start, that is where they are all start. Yes, Sir Philip, sir, there.
So if the phase value is the same and they have different amplitude.
Okay.
They're still in phase.
Yes, they are still in phase. So if they have different amplitude, of course, maybe one is going to go higher like this, and maybe it comes this way. Another one goes higher like this, then it comes this way. It doesn't change their phase difference. Is that okay? It's the amplitude that is changing. Phase difference is talking about where we are on the t, on the time. So it's like the track example that I used. If I am come to raise a child, I'm taller than the child 100 times, and we are still going on the same track. We may be in phase, but in terms of our height is different. Is that okay? So the whole equation is telling us the dynamics of the wave form and how it is behaving. But the phase here, we are talking about where they are starting and their point of the two waves on the wave. Let's see the sinusoidal form. Is that okay? That is what we are looking at here. So Sakodi, are we good? Perfect. And because they will all have the same value. Yes, say Sakodi.
I wanted to ask the reason why the sign over there is negative and not positive. Is there any reason?
The sign over
minus
here.
W. Minus
The omega. So can someone help me here? This negative that we have here. It can be positive, it can be negative in some books though. But do we have any idea why? So this is just talking about the direction of the wave. Is that okay? So some books they will just do it positive, some books they will just do it negative. It doesn't really matter. Is that okay? So it's just talking about the direction that we are moving with the wave. So, but that one is not related to the phase difference. That one ends here. The phase difference is the last one, the file that we have here. So here we call it file 1 or file 2. So the phase difference is talking about this. And you know, if phase 1 has a value of 2 and phase 2 has a value of 2, we subtract, we are getting 0. Is that okay? And if we get 0, we see the change in phase is now 0. So it means that they are in phase. Is that okay? So if they have the same value, ideally we will see that the two waves are in phase. Are we okay? Can I continue? Perfect.
Yes, sir.
Now let's talk about when they are out of phase. Is that okay? So when two waves are out of phase, it means we have no non-zero. Is that okay? So we have a value for it. And even when they are out of phase, how common is it in out of phase? Could they be out of phase up to 90, out of phase up to 180? Is that okay? And now we know that anytime we complete a full cycle, I start from here, take a half, take another half to here, I have a 2 pi. Is that okay? So it means that anytime we are talking about 180, 180 is half. So 180 reaches this end. So pi will be here. Do you agree to that? Perfect. Now, if we are talking about 90, 90 is going to be around this end. That is going to be pi on 2. So now we want to look at if the two waves are in phase up to 90 degrees, how the two waves is going to behave. Is that okay? It means that when it started, after 90 and another wave started. Is that okay? So it means this wave is going to start from here and it's going to move like this till we get to this end. So these two waves, they are out of phase of what? 90 degrees. That is quarter cycle apart. In a situation where we will say they are 180 phase of phase difference. Let me see if I can clean this so that I'll draw something else. Oh, I've cleaned everything, sorry. So here I have 1 here. 1 cycle here. We know this is 2 pi. We know the middle here is pi. We know this end is pi on 2. Now, if I want to do a phase of 180, it means I'm going to start from here, right? Then my wave is going to move like this. I think I have to use a different color. So it means I'm come to start from here, then move from here till I get here. So something like this, we will say we are out of phase of what? 180 degrees. Are we appreciating it a little? Perfect. So this is what the out of phase is just talking about. So now let's look at something here. So this is a typical example of the another 45. What I showed you earlier was 90. But another 45, it means that if I have a wave form like this,
I think the yellow color is not helping.
yeah, so I just realized, so I'm coming to change it. So let me use red. So if I have a wave like this, then the first wave is behaving something like this. Now, we know this end is 2 pi for a full 360. For 180, I have a pi here. For 90, I have a pi on 2 here. Now for 45, where is 45 going to be? 45 is going to be 45 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 going to be This is a question for the class. Where do you think 45 is going to?
So half of the
Half of
90,
the
slightly to the
first
left.
quarter.
Yes.
Very good. So it means I'll be going around this end. So here I have pi on what? On 4. Is that okay? So if the shift that I have here, for an example, that we are told that it is 45 out of phase, shift by 45 degrees, it means when this one started, 45 later, then this one started. So it means it's going to move along around something like what we have here. Something like this. And that is what it is drawn here. Is okay. So we have our phase 1 and phase 2. But this time around, they are 45 phase shifted.
Yeah.
Please, are we appreciating it a little? Perfect. Now let's do we can do a little calculation about these things if we are given some parameters. There's a simple equation where we can, if there's a phase difference, it means there's a change in time. Is that okay? That is why we have change in t there. And of course, there's also a change in phase itself. And we can relate the angular frequency there. If we have a situation like this, it's quite easy for us to know the angle that the phase has changed or the time that they started differently. Because if we have something like this and we know this axis is related to time, it means that when this thing started, the phase wave started, a little time came before the second wave started. Is that okay? It is different from the wave, the phase. The phase is talking about this whole scenario. Is that okay? At the point of that wave. But the time is talking about which one started first and which one started the second. So it means that is going to represent the change in t, and the phase is going to represent the change in the phi. That is the phase. Is that okay? And we have our omega here as the angular frequency. Now, we all know that we can relate angular frequency with period, where we have change in t on what? The period. Sorry, changing 2 pi on period. Sorry. So if I place the 2 pi on period at where the omega is or the angular frequency is, I'm going to get this equation. Is that okay? So what I have here, if I do change in phi, then I am dividing, so I can multiply, then just change bring the denominator up and numerator down. This is how it's going to behave. Then at the end of the day, I'll get my changing phase, my period on what? 2 pi. And that is what I have here. Is that okay? In simple terms. Are we good with this equation, the last one? Perfect. Now, it means anytime I am giving the period and I am giving the change in phase, I can find the change in time. Or anytime I'm giving the change in time and I am giving the change in phase, of course, I can find the period too. Is that okay? And vice versa. So there's a question here that I want us to try. This question, we are looking at the phase difference. We want to calculate for the phase difference, this one. And lucky for us, the question has given us some parameters which we are going to use. Is that okay? So if 2 waves of period, so we are giving the period 1, produces this time seconds apart, it means we are giving the time. What is going to be our phase difference? Can we try this thing right now? Like under 5 minutes. So write the equation, look at the parameters that it has been given to you, and see if you can find the phase difference for me.
Rosa. Rosa.
Yeah, hello. Any update for me?
Yeah, you get 45.
Okay. I am very, very interested in the procedure that you used to get that.
Sir, you get pi over 4 reading.
Pi over
You
4.
make the this in the subject. The change in phase of the subject.
Change in phase the subject. Okay.
So the formula is
So
going to
in making that the subject, you will get that means the change in phase is equal to change in time times 2 pi over t, which is the period.
Change in time 2 pi on t. Oh, okay. On t.
2 pi.
Okay.
On t, which is the period.
Okay.
When 0.025 is the change in time times the 2 pi. The pi is 180. So 180 times 2, 180 times 2 give you 360. 0.0025, that is the change in time. The 2 pi, the pi is 180. So 180 times 2 give you 360.
Okay.
So if you multiply 0.0025 times 360, then you divide it by 0.05, which is the t, will give you 45 rad.
Okay. Okay. That is perfect. I want a different answer. So there are two approaches. You can either change the radian to degrees and work around it like that, or you can just keep the radian so that you just keep the 2 pi like this. Is that okay? Then you divide it by, yes, sir. Please, I'm listening.
Yeah, that's how I did it. And I had pi over
That's how you
4
did
reading.
it. Pi over 4. So you get
So when you
pi.
simplify the 0.00625 over, you get 1 over 8. So 1 over 8 times 2 pi would be pi over 4 rad.
Perfect. So the two, they are correct. So when you have pi on 4, it's the same scenario that I did here. Pi over 4 is 45 degrees. Is that okay? So pi over 4 that we have here is in radian. So when you do this, the unit I beg is supposed to be in radian, right? Or if you go through how Selaki did, perfect one, you will still get the right answer. But that one is not going to be in radian. That one is in degrees. Is that okay? So that one, when you go through that one, you get 45 degrees. Are we all okay with this particular question? You see, it's kind of straightforward there. So this is quite simple. Madam Patience, Madam Ernestina, Madam Presla, how did it go? Sir Mohammed, I've not heard your voice today.
Pi on 4.
Pi
Sir,
on
I'm
4,
around.
perfect. Radio. You are not active today. Why are you somewhere?
I just settled down. I was somewhere.
Oh, okay, that's fine. Okay, Madam Ernestina, thank you. Sir Samuel, yes.
Sir, mine is a question. Sir, please, would there be any situation whereby giving us this question in the form of a graph form, then they will ask you to calculate or maybe use the graph to calculate the phase?
That would be a nice question, but I've not seen a question like that before. That would be an extreme level.
Okay, sir. So our level there, maybe
yeah. So it's possible. It could have been a very interesting question, anyways. But I've not seen a question like that sincerely.
Thank
you. Okay. So let's go on. Now let's look at what we actually have to do in terms of physical optics. You know, when I started defining wave, I was very precise. We have the sound, we have the mechanical, we have the magnetic and other things. And in terms of propagation, how they are perpendicular and they are parallel. Now, if we are talking about physical optics as this course that we are doing, we are very, very, very particular or interested in electromagnetic waves. Is that okay? So we are not going to consider the mechanical part, just the electromagnetic one. Very, very interesting one. And in fact, if at the right way, we should have done something like acoustics waves and other things, so that you also look at the other perspective of the mechanical, which could have been very interesting too. But we don't have enough time with this particular switch program, so we are doing our best for you to enjoy the other physics. Is that okay? Just in case in future you want to continue. Now, so all the conversation that is going to start from here is going to be particularly the electrostatic forms. Is that okay? Why did I keep on saying electrostatic? Electromagnetic forms. Is that okay? So it's going to particularly be electromagnetic forms of the wave. So now let's tell the conversation of the mechanical. Is that okay? And we are going and the longitudinal. We are just going to channel the energy, the rest of the energy on the electromagnetic and the transverse waves. Is that okay? Now, if wave, or let's say a ray of light is propagating, a typical one is some of the characteristics that we saw in relating the wavelength and other things. One thing that actually is important is this electromagnetic that we are talking about. We have the electric field and the magnetic field all propagating in perpendicular manner. Is that okay? Like the picture that I'm showing here. And I think the first slide, that is what I placed there, but I think it's a mistake because if I place it there, it will confuse students a little. I have to build a conversation before you see it. Now, if we have a ray, this is the direction that is going. And you see, for every ray, we have a wave moving like this. Is that okay? Which you understand the waveform right now because we've worked around it. And in the same phase and other things, there's another wave also propagating. But this time around, it is perpendicular to the first one. Is that okay? So you see where this first wave propagated, it is perpendicular to this one. Is that okay? And there are two fields that are working here, both the magnetic and both the electric. Is that okay? And in fact, the two fields name brought about the full name that we have here today as the electromagnetic waves. Is that okay? Now we will look at some of the properties later, but for now, let's continue with the general properties that we know and some of the examples, and we look at the spectrum. Now, let's take a typical example like the light. So you see, when light is also propagating through a medium, it behaves differently. When I have light, even a torchlight, and I on it under the water, and I on it when I move outside the water and I on it, the speed that is going to travel, they're all going to be different. Is that okay? So this also tells us that even electromagnetic waves in a medium behaves differently. Is that okay? So, and even with this one, I will explain it more when you are dealing with Snell. You see that if we are in a vacuum, no air, no gas, nothing, that is where we have light traveling at its maximum most. Is that okay? So anytime you see, when anyone asks you what is the speed of light, so 3 times 10 to the power 8 meter per second. Typically, when we are on Earth, it doesn't travel that much. Is that okay? It is only in a vacuum that we get light to travel that. But if we are even in water, it travels even more slower than we should be expecting. Is that okay? And even when we get another medium that has a higher refractive index, like a diamond, it travels way lower, like half of that was in a vacuum. Is that okay? So we are talking about 1.2 times 10 to the power 8, like way, way slower. Is that okay? So the medium that this electromagnetic wave is propagating through is very, very important. Now let's look at the electromagnetic spectrum. But before this, can I get a thumbs up with the explanation that I just did? Are we okay with that? I'm building a conversation, so I want us to understand. Okay, perfect. Now let's look at something that is also very important here. That is the electromagnetic spectrum. The electromagnetic radiation that or waves that we are talking about, it has different forms of radiations under them. Is that okay? We are talking about 7 radiations, and we're supposed to look at them individually so that you understand them. Now, if we want to understand the electromagnetic spectrum, there's a particular formula that we have to familiarize ourselves with first. Now, we have a formula like E equals HF. Have we seen a formula like this before? Okay, Frank Paddy has seen it before. Apart from Frank, who again? Oh, great. Now, yes, Sir Mohammed. Okay, so let's look at the parameters with this particular equation. What does the E represent? What does the H represent? What does the F represent? This is a question to the class, yeah.
E represent the energy.
Mm.
F is the frequency.
Mm-hmm.
And then H is a
H is the
constant.
Planck constant.
Perfect. So we have the energy, the Planck constant, and frequency. Is that okay? In fact, we can also relate wavelength, frequency, and velocity. Can you tell me the formula?
V is equal to lambda F.
V equals to lambda F. Thank you. Now, I am not interested in frequency here. I want to relate energy with lambda. So I'm going to get energy to be equals to H. If I make F the subject here and I bring it in here, what am I going to get?
V on lambda.
V on lambda. Perfect. Now, let's disintegrate this thing very well here before we go. Mathematically, anytime energy increases, what happens to frequency? This frequency.
It also increases.
It also increases. Do we all agree to that? Okay. So anytime energy is increasing, frequency is increasing. Now, mathematically again, anytime energy increases here, what happens to the wavelength here?
Decreases.
It decreases. Thank you. Now, let's look at something again. Let's shift the conversation to the electromagnetic spectrum here. Is that okay? So the electromagnetic spectrum is comprised of variety of electromagnetic waves. Is that okay? With different wavelengths and frequencies. These 2 parameters are very important here. So if we are talking about frequencies, we can also bring energy in here because they are related. But here I'm going to relate wavelength and energy particularly. Now, with the electromagnetic spectrum, we have the gamma rays, we have the X-rays, we have the ultraviolet rays, we have the visible, we have the infrared, we have the microwaves, and we have the radio waves. These are the 7 radiations that we can think about when we are talking about the electromagnetic spectrum. Is that okay? Now, the whole conversation starts from which one has higher energy, which of them has lower energy, which of them has a longer wavelength, and which of them has the shorter wavelength. That is the whole conversation here. Is that okay? And when you look at the waves that I've drawn up here, you can see that when it is getting to this end, the wavelength gets shorter here. Is that okay? When I say wavelength gets shorter, you know, anytime we start from a peak here to a peak here, we are measuring the distance of a cycle. And ideally, if we measure the distance here, it's going to be longer than measuring the distance from this end to this end. Do we all agree to that? Perfect. So it means that at this end, I have a longer wavelength. At this end, I have a very short wavelength. Is that okay? So when we are discussing it, we say shorter wavelength. When we are discussing it, we say longer wavelength. Or ideally, when you say shorter wavelength, we are saying lower wavelength. When you say longer wavelength, we are saying higher wavelength. But we don't say higher wavelength, we say longer wavelength. We don't say shorter, we don't say smaller or lower wavelength, we say shorter wavelength. So when it's short, it means it's low. When it's long, it means it's high. Please do you understand the terminology here? Perfect. Now, if we understand this, now let's move on. In terms of energy, the energy starts from here. You know, energy and frequency are related. So they are directly proportional. So anytime frequency is big, of course, higher energy too is big. And when we look at the frequency chart that we have beneath here, the value here, we have 10 raised to the power 20, very, very high. The least one is 10 raised to the power what? 4, very, very low. Is that okay? So it means gamma rays has a way higher energy than the what? Than the radio waves. Is that okay? Radio wave is the least one. Gamma rays is the highest one. And if higher energy is high, it means wavelength is going to be low. And I said we don't say low, we say what? Short. So it has a high energy and a shorter wavelength. Is it confusing? Or we understand?
So repeat it again.
Okay. So I am saying that with the electromagnetic spectrum, this is how it is arranged. We don't change anything. You can't bring ultraviolet first and bring this one second. No, how it is arranged, this is how we arrange it. Is that okay? It's supposed to be in order like this, either ascending or descending, but it's supposed to be in order like this, the 7 radiations. Now, gamma rays has the highest energy because when you look at the chart here, frequency has the highest here. Frequency has 10 raised to the power 20, and the least one has 10 raised to the power 4. And we know that frequency is directly proportional to what? Energy. So if frequency is high, it means energy is high. Is that okay? So if we have a very high energy here, it's going to be different from that of the wavelength because they are inversely proportional. High energy, we get lower wavelength. And now we are saying we don't say lower wavelength. We say what? Shorter wavelength. Is that okay? So high energy for gamma rays, but shorter wavelength for gamma rays. High frequency for gamma rays, but shorter wavelength for gamma rays. So the gamma rays has high energy, high frequency, but the wavelength is what? Is low. But this time around, we see the wavelength is what? Is shorter. Is it still confusing?
No, yeah, okay, sir.
Perfect. Now, let's move to the radio waves. With all the radiation, radio waves is the least one in terms of energy. The energy is very, very, very minor. Is that okay? So, I'm free. So, it has the lowest level of energy. But if energy is low, wavelength supposed to be what? Question to the class.
High wavelength.
Longer.
Very good. It's going to be longer. You will say high wavelength, but we are saying we don't say high and low with wavelength. We say what? Longer wavelength. Is that okay? So the radio waves has a very long wavelength, but in terms of the energy, very, very minor. Very small energy. Is that okay? Do we understand this? So anytime the conversation comes when talking about electromagnetic spectrum, I beg of you, relate these two formulas. Is that okay? Energy and frequency, energy and wavelength. You can, if you are even asked, you can literally write the equation, then try and relate it. But make sure you don't change how it is arranged. If you are starting from gamma rays, make sure you start from gamma rays to go to X-ray, go to ultraviolet, go to visible, go to infrared, go to micro, go to radio. Don't bring the radio, then come and bring micro later. Or don't bring the visible at the very last end. You get everything wrong. Is that okay? So whether ascending or descending, make sure it is arranged in this kind of order. It was from Pashamati, I say. Okay. Now let's look at the radiations individually. Now, when you are talking about a typical radio waves, like among all the radiation, that is what has the least energy. You know. Now, we sleep with our phones, we wake up with our phones. You are even making a call with someone, then you sleep with the phone. Then everything around us is radio waves. Now, the watches that we wear, the earphones or AirPods that we wear, they are all radio waves because it needs a signal from the phone, and it's not wire connected; it's wireless. Is that okay? So through the wireless connection, that is what the radio waves comes in. We use Bluetooth. Now the typical name as Bluetooth doesn't come in, but those who are using iPhones, they call something airdrop. This is also a form of radiation that is sending signals. Is that okay? So all the radiations that you get, any form of gadget around us, there's a form of communication among the gadget. Now, I use iPhone and iWatch. They've synchronized automatically through this radiation. I'm using a laptop here. It has also synchronized with it because when I get a call, it comes on the laptop straight away. The same radiations. Is that okay? Those who use it in their houses, they have smart homes. They are, let's say, their light is connected to the fan is connected to a radio somewhere. They are all connected. They all use these radiations. Is that okay? So the person enters a room. The person can even say light on, and the light goes on, light off, the light. They are all this form of radiation. A signal talks to pick it, but when it picks it to the server communicates to the rest of the gadget through what? These radio waves. Is that okay? And even our 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 hospitals, we still use radio waves. Is that okay? The magnetic resonance imaging, a typical form of a radio waves. Is that okay? It's very, very harmless. Now, but there's a limitation with the radio waves because it only has a level of area that is strong. It's like using a Bluetooth to pull something, When you are connected to the person's phone and you move away, when it's sending a file, it's going to take a little time before it sends the file. If you move outskirts of the radii of that particular signal, it stop sharing the file. Is that okay? If you get closer to it, the faster it's able to send the file. Exactly. And I don't know if you've observed this. Is that okay? So you have to be close to the radar, like you have to be in the same I don't know how the term to use. Yes. So the radar that it has created around it, you have to be in that radar before it works. And that is why you are listening to, let's say you are in Cape Coast, you are listening to Cape Coast FM. Then you are traveling to, let's say, Kaswa. Then you reach a particular end, then Cape Coast FM is not coming again. Then another signal just jump into it for you to listen by force, So it means you've moved outskirts to the radar of Cape Coast FM. Is that okay? So another radio station that has the same frequency as Cape Coast FM in that direction picks it up. Then you listen to that one later. Is that okay? Then you start listening to that one. You get to, let's say, Amasaman. Then all of a sudden, another radio station jumps in. You've not even asked it. Is that okay? So it means you've moved outside the radar of that particular radio station and you're in another direction. Is that okay? So it picks that one later. Then it moves on like that. Is that okay? So that is how our communication even works. So I pick a phone, I call you. There's supposed to be a closed tower around me. The tower picks it, sends the signal to another phone, send it to another tower. The tower gives it to you. Is that okay? They will be communicating like that. But this thing is very short. The time difference is in a nanosecond thing, so you don't see the changes in any difference. It comes as a real time. Is that okay? So we talk and you don't wait for some seconds to come before you hear me and I respond. We talk and it's very smooth. Are we understanding it a little?
Yeah.
Okay. Do we have to go to break and come back, or we can just continue and finish?
So please let's continue. My suggestion.
Okay.
Yeah, let's continue. There is some of our belief or chasers.
So, like, what did you say?
I said, let's continue.
Okay.
By community.
So, radio waves has a lot of advantages. Another wave that we can talk about is a microwave. And of course, when we say microwave, the only thing that comes into mind is the machine we use to heat food. Is that okay?
Yes,
So,
in the kitchen.
yes, in the kitchen. We use it a lot. Is that okay? But apart from that, radio waves too has.
But I'm patient and food.
It's very important. Food is very important. That is what comes into mind. But apart from that, radio waves too has a lot of application. Right now, some of the phones even don't use radio waves; they use microwave rather, and it's literally the same thing. The GPS trackers that some of people wear, even the broadband. You see, right now MTN has something that you can go and buy, like a router. Then you buy, then you plug it. Then within a particular locality, it serves you Wi-Fi. So you buy I think monthly or something unlimited. Then you buy the bundle on it, then you'll be using. So it's something like buying a Wi-Fi for your house. So this time around, you and your family are tapping into it. All these things uses radio waves. Is that okay to give us the data or the internet that we want? Or when you go to even some offices, they have Wi-Fi, they just tap on it and you go. They are all radio waves. Sorry, microwaves. Now, the food that we have, it is just a small chamber like this. Is that okay? Then there's a little plate on it. Then you put your food on a plate or a ceramic thing. Then either cover it or not, you just place it in there. Now, what the microwave is doing is from one end here to another end here, it sends some signal. Is that okay? And the signal is in the form of a radiation or the waves that we spoke about. Is that okay? From this end, and it goes to the other end here. And the working of the microwave we have in the house is very simple. Its own is to vibrate water molecules in the food. And I think I've mentioned this to the class before. So in the process of vibrating the water molecules in the food, it heats up the food. Is that okay? And the vibration is a lot of vibrations within some seconds. Is that okay? So friction, how friction works and other things. The more it vibrates, the more we get heat in the system. Is that okay? So sometimes, if you've observed, if you put a very dry thing in the microwave, you don't get it heat up. If there's no water molecules inside, you put it in and you have to remove it like that. Is that okay? If there's no water molecules inside. But in a situation where there's a water molecule inside, voila, the microwave works perfectly. It will just vibrate and it will get the food heater for you. Interestingly, when this microwave started coming, now the microwave that we have, the thing or the plate that you put it on, you put your food on, it rotates. Madam Patience, right?
Yes, sir.
Very good. So it rotates. First, it wasn't rotating. And when it wasn't Please hold on. Oh, okay. Hello, can you hear me?
Yes, sir.
Okay, perfect. Thank you. So it rotates because first the microwave wasn't rotating. So you get you take the food out of the microwave, then some part is heated, some part is not heated, and other things, So now this because the radiation that is moving in the chamber, or let's say your microwave, it's coming in only one direction to the other direction. It doesn't circulate in the chamber. It doesn't have that ability now. Is that okay? So the only thing that we can do so that there's going to be a uniform distribution in that radiation is to rotate the food. Is that okay? So now all the right microwave that comes inside, they have a flat glass inside. Then under it has a small thing that sits on it that can rotate it. So when you put your food on it, you put it on that glass, then that glass rotates. In the process of that glass rotating, your food in the bowl also rotates, and there's going to be a uniform distribution in the radiation. Is that okay? So at the end, literally every part of the food gets the radiation and it heats it up perfectly for you. And it's not harmless. It's 100% harm-free. Is that okay? As of now, there's no research showing that radio waves and microwaves are harmful. Like they are 0% harm-free. Is that okay? Nothing will happen to you when you get contact with. You've been living with it forever. So if something will happen to us, okay, is that okay? So it's very, very harm-free. Can we go on? Another one is the infrared. And I think I spoke about the infrared thermometer and even this thing that we use, the remote that we use, they're all infrared. And in fact, every body emits an infrared radiation. And the last time I was telling, I don't know if it was your group or some different group, I was telling them that one researcher from chemistry department brought a light source to our department. So sometimes we do these kinds of testing for different people if they have an issue with that research. So they brought a light source and they wanted to look for the wavelength for the light source. And I was the only one there as at then. So I think as at that time I was doing my master's. So I sent it inside, plugged it in, then I on the light source, and nothing was coming for me to see. You know, when we on light, we want to see red, we want to see green, we want to see yellow, we want to see white, you know. Then nothing was coming at all. So I was so confused. All this, I was thinking I've spot what they brought. So later on, then my colleague came and he said, "Oh, light and also, but me to me from any because it is infrared." Exactly. So the infrared radiation, our eyes will not be able to see it, but it emits. There's a radiation coming out. Exactly. So we have different form of detectors that can see this radiation. My slide, Madam Patience is saying my slide is not showing. Is it for everyone or only Madam
Yeah,
Patience?
it's there.
It's for everyone.
It's there, but not clear.
Okay. I'm trying to use the house Wi-Fi and I don't know why it keeps on disappointing me. Please, what about now? I've switched. Is it clear
It's
or
still
it's still
blurred.
not clear? It's
It's
still
still
blurred.
blurred.
Not clearly. Mm.
Yes. So Mohammed, can you give me a feedback?
Sir, I think it's better now.
Okay. Madam Patient, what about you? Or it's still blurred?
It's better than before, but not.
Excuse me a minute. Let me switch it.
So please, it's okay now.
I've even switched again. I don't know if this one will be better.
Yeah, it's okay, sir.
It's okay. Okay. So now, the whole point of this conversation is infrared is not something we can see. We need different form of detectors. Now, even the cameras that we have in our houses, the security cameras that people buy, some of them is also has infrared sensors inside. So even at night, if the person off his houses or you find ways to off his like the entire house's lighting system, the camera can still work perfectly to detect an individual or an intruder coming in. Is that okay? So that is how technology has sent us to. We can detect these things. And even when missiles are coming, you heard about this war and other things, and you see, they will say Iran or Israel has launched a missile and this one has dismissed the missiles in the sky and other things. It's all through this radiation because when the missiles are coming, it's also brings a form of radiation. Is that okay? So if you're also on the ground and you have a detector that can reach or detect this kind of radiation, it means you can also fight against anything that is coming from the sky because as it's coming, it takes time before it reaches you. Is that okay? Because it's flying to you. So before it comes, if you can detect it from a distance, you can stop it there. And Dubai, I think, was doing a very wonderful work with this. I think their technology level is very high. Ghana here, when they launch missiles here, we all die because our technology system is that bad. Is that okay? But they are good enough, so they can dismiss everything that is coming. Is that okay? So we pray that something like this doesn't come to us. Else, you know, you just say you could two who to a punim, a janico soon. So let's go. So the infrared thermometers are very important. Is that okay? And let's go to the almighty visible light. Visible light is part of the radiations in the electromagnetic spectrum. That one we can see. You can use your eyes to see. I can use my eyes to see. Is that okay? And that is the white light that we have all over. Is that okay? So the white light, even the sun is helping us. Is that okay? The sun helps us to get light to what? To also see. So, but light too can be dispersed into different components, which we'll be looking at it very soon. So we've matched all the colors to get the white light. Now, if we are not interested in all the colors, we want a particular color too, we can disintegrate it and pick only the red one, or the violet one, or the blue one, or the green one. Is that okay? And they all have their wavelength. You remember I mentioned shorter wavelength, longer wavelength. They all have values there. Is that okay? So we can relate the white light colors with its respective what wavelength. And please, this thing you have to know. At least, if not in details, you have to know that, okay, when you talk about violet, we are talking about 400 nanometers. When you're talking about red, we are talking about around 600, 700 nanometers. Is that okay? You knowing it detailed, maybe it's not necessary, but at least know where violet falls, know where blue range falls, know where green range falls, yellow, red, and orange. I beg of you. We have to do this, but I'll come back to this later. Is that okay? I'll come back to this. Now, UV radiation. UV radiation too is very important. I think UCC here, particularly when you are coming here, they let, I don't know if they did some too for switch, but if you're a student, you're coming in first year, you have to do medicals. And in the process of medicals, you have to go and take your x-rays. I don't know, did you do something like that? Sir Mohammed says schizo.
No, please.
No.
Oh, okay. So you pass through all the. You have to go and check your eye, your teeth. You have to go and see a doctor. They have to test you, your blood and other things, before you actively start the academic calendar, academic journey. So I don't know why they didn't do for switch, but ABA a or maybe you will not get time. That's why maybe they didn't do it. But I'm defending UCC. But anyways, so UV radiation is is very important. You can imagine the fact that I have a particular radiation. Is that okay? And the radiation can pass through your body to determine what is inside the body. Very, very phenomenal and very, very interesting too. But before we go on, let me show you something. Madam patient tested something, but I couldn't read it. I don't know why when I want to read it vanishes and I
So
don't
it's
see
not
it.
necessary. I was talking about the teeth. Going to examine your teeth.
They have to see. I've already removed some
What
of my
for?
molar teeth, so they will count if you have the same number of teeth as a usual human being. No, I don't know why they are checking these things, but they check your teeth, they check your eye, they check your x-rays, they check your blood. So sometimes it helps because some of the students, when we are coming, we don't even know our blood group and other things, whether we are sickle cell or not. So when they come, the university gives you the opportunity to check these things. But it's good they have to also know, because when you even travel outside the country to school, you have to pass through some medical procedure before you go. So they check all these things. Before I move on to x-rays, let me show you something. With the visible, what do you think is harmful? If a visible radiation hits my skin and a radio wave hit my skin. Which of them do you think will harm me more?
Visible.
Very good, visible. Please, do we understand?
Yes, please.
Yes,
It has high energy.
Very good. Because it has high energy. So you see, that mentality where people sit on social media and say, when you use your phone, you get cancer, then the person shouldn't pass through the sun. Because the person shouldn't sit under the sun, under a light in the room. Because that one rather will give you more cancer than even the radio waves or the microwaves. Is that okay? The mentality about microwaves giving you any cancer diseases maybe the plate you are heating your food in. Is that okay? Where there's going to be some leakage of some microplastics inside the food. Because when you're using a microwave, they are very specific with the ceramic plate you have to use or the rubber plate you have to use. Some rubbers, they've written non-microwavable. Some of them, they've written, but I stand to be corrected. Madam Patient, it's right?
Yeah. You use
Yeah,
the
they say
ceramic
this thing,
bowls for the heating.
and the
Yeah.
heating,
But you
you
don't
know,
use the
and
plastic
so they will be
ones.
very good. So even the plastic, they have some of them, they've written on it whether you can use it to microwave or some
Yeah,
of them you
that
cannot
one
use to.
is the silicone ones.
Okay. Exactly. So they are very specific about this, and whether you can use aluminium for use. That is where the disease issue comes in. But the radio waves itself, zero harmful. So when someone sleeps and at the end of the day the person sleeps with the phone and additional, it has nothing to do with microwaves. Or no, is that okay? Maybe some electrical stuffs happening on the phone or in the phone, then something happened. Is that okay? Then it got bent and it affected him, and maybe some cardiac arrest happened or something. But the radio waves itself, zero effect. Is that okay? So as we know this now, anytime some people talk about it, let's use the physics to educate people about it. Is that okay? So that at least they know what is actually going on. If they argue, they shouldn't pass through the sun again. They should create their own chamber and use the chamber to walk around. Now we are moving to higher energy like the UV radiation. This is harmful because it has higher energy than even the visible energy. Is that okay? In fact, those who take your X-rays, I think I've done a CT scan before. And CT also is about this UV radiation. They have a chamber that they will put you in to take the scan, and they will go and sit in another chamber, that is lead protected and other things, so that the radiation doesn't come to them. So you will sit down, then you take your scan, then they will be in the control room to control the machine, take your scan, and you finish, they will come back, then come and you go and undress and other things. Exactly. So this is also very important. So the radio waves is harmful. Even under radio waves, we have one we call the hard, and we have one that we call the soft. When you're looking at X-rays, hard X-rays and soft X-rays. When you are traveling to, you don't necessarily have to open your bag and empty every single thing for individuals to check. That is going to waste a lot of time because already the airport, there's a lot of chaos there. A lot of people are traveling. So there's no time. So what you do is you just drop your bag on a trail. It enters into a small chamber. It gets it scanned. Someone is behind the PC monitoring what is going on. Any anomalies there, the person will bring it up that there's something going on there. Is that okay? And it's interesting that you've closed your bag, no matter how heavy and sealed the bag is, the machine is able to know what is actually inside. And it's because of these radiations. Is that okay? It sends a signals and it gives a feedback that you know what is inside. It's like you go to the hospital, then the doctor x-rays, it hits your chest. Then at the end of the day, it's able to know what is inside your body. Whether you have gotten a fracture or it's not gotten anything, the doctor tells you, oh, you are okay, you are not okay, let's do this, let's not do this. Exactly. So it is very important. A lot of applications of them. And in hospitals too, phenomena, doing a lot of work. Even in research, we do this X-ray spectroscopy. Is that okay? In food security and other things, we check all these things. Is that okay? So X-rays is doing a very wonderful work. Now let's go to gamma rays. Now we are moving to higher energies. You know, the X-rays, they are harmful one way or the other. You cannot be exposed to it to a particular level, particularly when dealing with this hard X-rays. Because when you're even in the hospital, and let's say you are sick, and you go and take a scan, and let's say the doctor is not very convinced about what is going, and you have to take another scan. The doctor may advise that you take time a little before you take the other scan, because you can't be exposing yourself to the radiation a lot. Yes, I are now, yes, I for you know. So you have to wait, give it some time before you go and take another scan later. Is that okay? And it's very important. At first, there was something that was happening in I think US, one of the big mining companies. And what the company was saying that black people comes there, then they die early. So they were mining this one of the radiation underground. Then what they do is, you know, all those who work in radiation sectors, they wear a detector count on their chest. And what the count is doing is it has to read the number of radiations that the individual is getting exposed to. So maybe within a day, it counts like 100. It means I have been exposed to 100 radiations. If I have been exposed to 100 radiation, the chances of me getting about 95 in my body is high. Is that okay? So every company was having a limit or a threshold that the count reaches, and you have to go to the house. So let's say my account, the threshold is 250. When my account reaches 250, automatically I have to take a leave out. Then go and stay in the house like a vacation thing, so that the radiations disposes out of my body. Is that okay? So it gets disposed, then I'll come back, depending on the count that it has been exposed to. If you have to stay in the month, 1 month, 2 months, 3 months, 6 months, then you come back to work again. And it's very important. All the radiographers, they have this counter that they wear. So if you have a family member, maybe you can confirm from the family member, because it is very important. It's either they wear the counter, or if they don't wear it, anytime they are taking a scan, they sit in their chamber and take the scan, because if they don't take care, they are killing themselves one way or the other. So the company outside realized that anytime these black people, you know, blacks, we go to different country, we work and kill ourselves like nothing has happened before. But in our own country too, we don't work like that though. Then they come there, then as they work, like nipa neba and then the person, some random sickness, then the person just die, some random liver failure, random kidney issues, the person die, organ issues. So they realize that when blacks come there, they hide their account. Is that okay? Because you know how white do they work, the number of hours you work for them, they pay you good. Now, if you tell a typical black like me who is in US to hustle for money to build a house in Ghana, that I should go and stay in the house for 3 months vacation, what will I eat? What will I send to the family? So what they do is they hide their counter. So now the counter is not reading the amount of radiation he or she is exposing himself to or herself to. So at the end of the day, if the count is supposed to read 250 to take me home, right now, I'll hide it and I'll get exposed to about 1,000 radiations of counts. But at the end of the day, you know, a lot of radiations causes a lot of multiplication of your cell or the depletion of the cell, 2 ways. So you start developing something like a tumor, and at the end, long run, you start getting something like cancer, and at the long run, affect one of the organs, and long run, you have to die. Is that okay? Chemotherapy is there, but you still die if you don't take care. So that was what we, the blacks, were doing there, and that was what they actually observed. So the radiation is that harmful. Is that okay? So even if you know someone, you visited the person in the radiographer workplace, and the person is working, you have to give the person some space, move away from there, let the person do its work. Because if they have to be around, they even have a lead jacket that they wear so that their body don't get exposed to the radiations. You are not like that. You get exposed, and later on, some weird sickness will come and kill you. Exactly. You may think it's family, but no. It's your own reckless life. Exactly. So let's be careful about these radiations. It's very, very harmful. Exactly. So the gamma rays, also the gamma rays too is also very important. In fact, we can use it to generate energy, electricity, and other things. Exactly. So, and even some quality checks in blocks. You see, when you build a house, the engineers have to come around to come and check how strong the house is as of now, and if people can even stay in. And interestingly, they use these kinds of radiations. Exactly. So they just come and have to send a signal to the concrete and see whether it's bouncing back or it's not bouncing back or it's going through. And they use their own mathematical ways to prove whether the concrete is strong enough or it's not strong enough. So the application is a lot. And even in sterilization, when you go to the barbering shop, we the men, after they've used the machine to crop our hair, they put it in a UV sterilizer. Have we observed that?
Yes, sir.
So Mohammed, when they place it in, do you know what it does?
Just to sterilize or kill any bacteria or infection that might come to the shaving machine.
Okay, that's perfect. So basically that is what is doing. Very important. They have to sterilize it. And even right now in hospitals, they don't they don't uh, they don't clean these this instrument that they use for surgical procedures. What they have to do is to sterilize it, like put it under a small chamber. Then that is all. Send some radiations there, and it kills all bacteria there, which is very important. So radiations applications, they are too wide. Now we move to, so this is the gamma, and I think the last one is the gamma, and we end at gamma with the radiations. Any questions so far with the radiations before I move to the light matter interaction? Does it mean we are all okay so far?
Yes, sir.
Yeah, please, just a quick one. You said the gamma ray can be used to generate electricity.
Yes.
Okay, I don't know how possible it is. Maybe okay. I think
Radiations are energy. Even the light can able to generate electricity through solar panel. Is that okay? The normal light that we are having. Is that okay? When we use a simple like this thing, solar panel, the panel works as a PN junction and you get to electricity generated. Very, very simple. But in terms of the gamma, mechanically, I don't know how it can be done. But as far as we have high energy in a material, is that okay? Electricity generation is really possible from that perspective. Is that okay? Yeah, so lucky. So you can Google about it, then check it online too. But mechanically, I don't know how the electricity generation is possible. But as far as we are able to generate even electricity from even normal light energy that don't have high energy as a gamma, I know it's possible to generate energies there. And in as much as gamma radiation too is harmful, when people go for chemotherapy and other things, they can use this gamma radiation to heal the person too. Is that okay? So let's say you've developed some level of tumor, the gamma rays can be used to kill that if there's faster multiplication of some cells there. So there are level of importance there. There are some level of harmfulness too also there. Is that okay? Can we go on? Okay. But the 4 hour street is not easy. The way I've been checking time Time on Drew, baby. Yeah. Whoa.
But
I
we
don't
are
know if
almost
he's the
through.
teacher. Yeah, we are almost true. I don't know if he's the teacher, only the teacher suffering or the
We are
students
almost
too are suffering.
No, we are all
We are all
suffering.
suffering.
we are all suffering.
I've been checking time too.
We are all feeling the pain.
Uh,
The only thing is that you are talking in the morning, but we are
yeah.
all it
Okay.
is
You
well.
needed to have at least
Yeah.
10 minutes water break. Be.
Yeah, we should have gotten some break, but it's fine. I think we are almost through. So
Yeah,
let me
almost.
try and finish this section, then I'll end the class. So now let's look at light matter interaction. So now, when all the radiation that we spoke about, right? Now we are going to drop radio, we are going to drop micro, we are going to drop infrared, we are going to drop UV, we are going to drop gamma. Then we are going to focus on only light. Is that okay? Only light. The visible light. Let me go back and show you. So I am dropping all of these things: gamma, X-rays, UV, infrared, micro, radio. I'm interested in only the visible. Is that okay? I'm going to focus on only the visible. Now, when visible light hits on a matter, in fact, a lot of things do happens. But coming to think of it, if the class is not something that you are really into it, you may sleep within these 4 hours. Oh, and because 4 hours and
Yes.
let's say you're not following up water. Oh, interesting. But I hope you guys, you are not sleeping in my class.
No, as for the morning, there you don't sleep. But the second one, the
Energy
second
is there.
phase, you will see people sleep.
Yeah,
I always
you
sleep
are
during
tired
that
already.
time.
Then I'll always vouch for morning class so that Madam
Oh, that's
patients
the
don't
best.
sleep in my class.
Yeah, so but the second phase, there is no easy. You don't know that you are
Sorry.
sleeping.
We will finish right now, right? I think it's left with only one block, and we are done for everything, right?
Yeah.
Yes.
After this block, the next block, what will you school? What is
Yeah,
it?
then we are done.
We finish right now. Okay, let's finish that. So when light hits on a matter, a lot of things do happen, and some of the things happening is what I have listed here. Is that okay? It's either when light hits on a matter, reflection happens, or refraction happens, or interference happens, or diffraction happens, or absorption happens, or lastly, scattering happens. So some of them that I've listed here, we are familiar with it one way or the other. So we are familiar with the reflection, refraction. I think interference too. We all know interference, right? If you don't know, it's fine, I'll teach. But do we know interference? Can I get a thumbs up if you know interference? Okay, Frank knows interference. Apart from Frank, okay, that is fine. What about diffraction? Okay. What about absorption? Okay, that is fine. So we will go through all of them literally. Is that okay? So I'll first take with the reflection. Then the reflection we will just brush through because most of the things we've done. Then we'll jump straight to the refraction. Then we start moving from there. So now with the reflection, we all know how reflection actually works. We need an incident ray and we need a reflected ray. And at the end of the day, there's supposed to be a surface that the interaction is going on there. So if I am standing here and I incident a light on a material, is that okay? I expect it to hit the surface and come this way. And anytime something like this happened, in between the two of them, I have to draw a normal. Is that okay? And I have to draw a normal so that the angle here and the angle here becomes the same. Very important. Now, a situation like this actually depicts the law of reflection, which talks about the fact that if we have a surface, the incident ray, the reflected ray, and the normal all at the point of incident lies on the same plane. And another law talks about the fact that this angle is always equal to this angle. Always, no matter the situation, for reflection to actually happen, the angle here should be always be equal to this angle. Now, we can also divide or categorize reflection into two, where we have the regular and we have the what and the specular. Oh, sorry, the regular or the specular, and we have the diffuse or the irregular. Is that okay? So either you see specular reflection or diffuse reflection, or you see regular reflection or irregular reflection. So a typical one like this is what we have, the specular or the regular. And something like this is what we have, the diffuse or the irregular. Now let's look at something. Anytime we are talking about the specular, when light hits the surface, a parallel beam hits the surface, we expect the same parallel beam to leave the surface. This is for specular. So you see, this is the normal of this one, normal of this one, normal of this one. They are all behaving the same. So the angle here and the angle here, they are the same. The angle here, the angle here, they are the same. The angle here, the angle here, they are the same. Is that okay? So the parallel beam hitting the surface should be the same parallel beam leaving the surface. But in a situation where we have the diffuse, you see we have a parallel beam hitting the surface. But under no circumstance will we get the same parallel beam leaving the surface. Is that okay? They are going to pass anywhere that they want to pass. Right? So here you see the normal will be around this end, normal will be around this end, normal is going to turn around this end, normal is going to move around this end for this. Exactly. So this is a typical irregular reflection, and it's because of the microstructure of the surface that we have.
Please, sir.
The surface is
Please,
very, yes, sir.
in that case, would the angle of incident be the same as the angle of reflection for the rough surface?
That's a nice question. But let me push it to the class before I come in. Class, please, what do we think is going to be?
The same.
Can you justify it for us?
Yeah, because I think the law works for all the types of reflection. So at any point on the rough surface, the normal will be created in such a way that it creates equal angle of incidence and angle of reflection.
That is perfect. The law works for the two of them. Is that okay? Whether diffuse or specular. But this time around, you see how here you will get the normal, or the normal to be straight like this. That is perpendicular to the surface. Here, because the surface is rough, the normal is not going to be all straight as we have here. So you see this one, the incident comes in here and move out here like this. So the normal is going to be around this end. Here, the incident comes in here, then move out like this. The normal is going to be around this end. So when I say around this end, I mean the angle here is the same. The angle here, the angle here is the same. When you look at this ray, the normal is coming in here, the incident is coming in here, and the reflected is going here. When you look at a situation like this, if you want to get the same incident angle and reflected angle, it means the normal is supposed to go around this end, so that I'll get the same angle here as the same angle here. Right. Now let's look at the last one. Incident is coming here. It is reflected around this end. My normal is supposed to turn and come around this end. So you see, I'm going to get the same angle here, the same angle here. Now, the only situation is here, supposing the angles was, say, 45, 45, 45. The angle leaving out the reflection is going to be 45, 45, 45, going to be the same. But here, the difference in angle is going to be among the different rays. Is that okay? So let's say ray 1 for 2 for 3 for 4. They are going to have different angles. Because you see the ones here, the angles are bigger than the last one here. But for a particular incident and reflected, the angle is supposed to be the same. So this angle here is going to be the same as this angle here. This angle here is going to be the same as this angle here. This angle here is going to be the same as this angle here. This angle here is going to be the same as this angle here. And it's good you've brought this question up. Very nice question. Please, do we understand?
Yes, sir.
Yes, sir.
Now, another man also came into the picture. Snell did a very wonderful work. The fact that I place something in water, then it bends, or if light is traveling in air, then it enters into a liquid, then the speed of it literally slows down. It is mind-blowing. So what is actually going on in the water that is able to reduce my speed? Is that okay? Now, that is where the terminology as refraction came in. Now, what was observed was that anytime I incident light on some sample, instead of getting the reflection, I don't get a reflection. The light rather enters the sample, right? And it depends on something we call the refractive index of the sample. If one has a refractive index that is different from another one, there's a change in how the incident and the reflection is going to happen. Or in this situation, the incident and the refracted is going to happen. So you see, we are from air. Air has a refractive index around 1. We enter into water. Water has a refractive index around 1.33. So literally, the water is denser than what? Than air. Anytime you have a situation like this, if incident ray enters the water, ideally, we expect it to go straight like this. But because it is denser than air, it tends to bend closer to the what? To the normal. Is that okay? The same situation. If we are traveling this time around, I am underwater and I have light and I'm moving it outside the water. So I am inside the water here. If I incident the light on the surface, I expect it to go straight like this. But because I am from a denser medium to a less dense medium, the normal tends to what? Move away from the normal. Is that okay? The normal will only approach you when you are strong enough, you are dense, and it will approach you like the first scenario here. But if you are not dense, it will reject you. Is that okay? Like you have entered into air, you are not dense enough, so it will reject you, move away. Is that okay? And that is what refraction is telling us. Now, the law of refraction too is there. Then we can also relate something like the refractive index, as I mentioned earlier. Now, if I want to find the refractive index, what I have to do is I have to find the speed of light in the air. Then when I finish, I'll go and place the speed of light, go and find the speed of light in that medium, let's say the water that I'm dealing with. And if I divide the two of them, I should get the refractive index of my material. Exactly. That is the medium I want. The same way I can use the wavelength. So if I have the wavelength of the air and the wavelength of the medium, exactly. So keep this formula in mind. This is our first formula with respect to refractive index. So this is the law of refraction. And let's look at this, the second law. This equation is also very important. You know, we are moving from one medium to another medium. So this is medium 1. This is medium 2. This medium particularly has a refractive index. The second medium 2 has its own refractive index. The first medium has its angle. The second medium 2 has its angle. Now, the refractive index that we have here can be related differently because from our previous equation, I told you that refractive index is what? N equals CV. This equation, this one. So N equals C what? V. Now, if I come and place this N equals CV in here, it means I have C on V1 and C on V2. Now, the speed of light in air ideally is the same. So I can cancel C here, cancel C here. Now, at the end, they have 1 over V. So that is what we have here. Okay. So 1 over V sine 1 equals 1 over V2 sine theta 2. Please, are you okay with the last equation? Very good. Now let's look at something here. Let me try and see if I can finish total internal reflection. Then we will rest for the next class. Now, total internal reflection too is an important phenomenon, like very, very important. Now, if ideally, let's take only this scenario 1. I'm from a denser medium to a less dense medium. And anytime there's a moving from a denser medium to a less dense medium, it moves away from the what? The normal. This is my normal. Now, if it moves away, this is how it's going to behave. Forget about the B, the partial reflection. Forget about it. Now, let me ask the question, the class a question. Supposing I increase the incident angle to this end, what do you think will happen to the angle of refraction? This R.
So it will move away from the normal.
Perfect. It will move away from the normal. Is that okay? So it means the angle of refraction will increase. And that is what is going to happen. So if I move away again, it means it will also move again. So it will move out so it comes in line exactly on the Y. And now the point that it's lying on the Y, what is going to be the angle of it now? Question to the class.
90 degrees.
90 degrees. Now a situation where we have the incident angle moved to a point and the angle of refraction is 90 degrees. That is where we call it, this incident angle, we call it what? Critical angle. It doesn't become incident again, it becomes critical angle. That is the point that we have the angle of refraction to what? 90 degrees. This is very, very important. Now, that is where the second scenario comes in. So now we've moved the incident angle out to we get to what? The 90. Now it's lying on the Y. Now again, when I move it to exceed the critical angle, what do you think will happen to the angle here that we have now?
It will increase further.
It will increase further.
90.
It will be more than 90.
Is that okay? So now, this time around, it's going higher. And when it goes higher, it means, you know, all this end here is one surface. This one is another medium. Now, anytime it goes beyond, it means this time around, it is reflection that is happening. So let's say it comes here. So if it has not entered the medium, refraction is 0. So now it has moved outside the medium. So it means a typical reflection is happening. And that is what we have at this scenario. So anytime the angle of incidence is greater than the critical angle, we should be expecting reflection. Is that okay? We should be expecting reflection. Now, if we have a situation like this, that is where we have total internal reflection. So in the process of refraction, do but we've gotten what total internal reflection. Now we can relate some formulas to it because we know this formula already from refraction. When we substitute, we can make this by making n the one subject, then dividing both sides by sine I. Then when you finish, divide both sides by sine r. So from the denser medium to a rarer medium, if we are talking about water and let's say air, we know the refractive index of N2 is 1. We can write 1 here. And because we reach a critical angle, we can make the angle of refraction become 90 because we know the angle now. So sine 90 is going to give us 1. So we write our 1 here. Then now we bring our sine I, which is the I is now critical angle, so C. Is that okay? So now this is very important. Now it means that I can find the refractive index of my medium if I have the critical angle. Is that okay? I just need the critical angle and I'm good. So I can find the refractive index of this particular medium if I have the critical angle. And that is all. So keep this formula to in mind. This is our second formula with refractive index. So relating refractive index and critical angle. The other one was relating refractive index and the velocity. Any questions so far? I'll try and update the slides with some questions so that we will appreciate some of the things we are doing so far. But the next time we meet, we will look at interference, the absorption, refraction, Huygens principles, pull and position of waves. Then, we didn't even finish unit 1, interesting. Then you move to unit 2. Then we come and do interference proper here with the formulas. Then thin film interference. Okay, unit 2 is not plenty, so we may finish soon with unit 2. Then we move to unit 3. Tana and the class for today. Yes.
I think we have already done the interference and its calculation.
Yeah, all the things that I'm teaching, we've done it before.
Okay.
Yeah, we've done. I remember I taught. If I'm the one who taught in introductory atomic heat and optics, I've taught all these things. But I know we've forgotten. That's why I've taken my time because it's in a syllabus that we do. That's why I've taken my time to trade.
Okay.
Sir, please,
If the
when
class
are we
wants me
getting
to
the
jump, I
slide?
can just jump again. Is it?
Please, when are we getting the slide?
I'll just do some small updates and send it to you within this week. So,
Let it be this week.
it will be this week, madam.
Yes.
Excuse me. Kindly remind me by Wednesday, then I will send it to you so that you send it to the group for me.
All right, sir.
I appreciate it. So have a nice evening. My tummy is rumbling for breakfast, so we'll meet God willing next week. At least we have some more time to rest before our next class. Okay. Bye-bye.
Bye.
Thank you very much.